Have you ever wondered why old ships have such a powerful, enduring presence? It's not just nostalgia. It's because they were built on a different principle. You see, old ships weren't built because someone did the math and figured they could survive the sea. They were built because everyone involved assumed, without a doubt, that the sea would eventually try to kill them. It meant the keel went deeper than strictly necessary. The frames were thicker than what was considered efficient. The hull plates overlapped like scales of armor, riveted by hand in patterns that looked excessive even to the men who installed them. The shipwrights didn't just trust equations on a page. They trusted memory. They remembered storms that came in sideways, waves that lifted steel as if it were a piece of paper, and nights when the horizon just vanished, leaving the ship as the only reality in a world of chaos. Back then, reliability wasn't just a performance metric you checked off on a list. It was a philosophy born from fear, respect, and a deep, hard-earned humility. Think about it. If a ship failed at sea, there was no customer support email to send. There was no warranty to claim, no replacement part arriving in 2 days. Failure meant water flooding into places it shouldn't be. It meant fire where it couldn't be controlled, or a sudden, terrifying silence where an engine's steady heartbeat should have been. So, the builders leaned into margin. They added weight, because weight meant inertia, and inertia meant the ship wouldn't flinch at every insult the ocean threw its way. They willingly accepted inefficiency, because efficiency was fragile, and fragility at sea was simply unforgivable. If you could walk the length of an old hull in your mind, you would feel this thinking embedded right into the metal. Bulkheads weren't just there. They were numerous, spaced close together so that flooding one compartment didn't automatically become a death sentence for the entire vessel. The pumps were oversized and duplicated, not because someone modeled the statistical probability of failure, but because someone had once watched a single pump choke on debris while the water climbed relentlessly up the ladder rungs. The valves were manual, heavy, stubborn things that required real muscle and intention to move. They didn't care about a power loss. They waited patiently for a human hand. There was this quiet, unspoken understanding that the sea was an adversary that never, ever tired. So, these ships were built to endure not the average day, but the worst imaginable one. Storm survivability wasn't a footnote in the design brief. It was the absolute baseline. Every detail reflected this. Deck fittings were the coamings around hatches stood tall and proud, high enough to keep a boarding sea from pouring straight down into the ship's belly. Even the lifeboats were built like small ships themselves, because abandoning the mothership was never assumed to be a quick or orderly affair. Old ships also wore their scars openly, like a seasoned warrior. A bent stanchion wasn't immediately ripped out and replaced. It was straightened, reinforced, and remembered. A crack appearing in a deck plate was stop-drilled and patched, not hidden under a coat of paint. Every repair added character, but more importantly, it added knowledge. The crews learned where the ship complained first, where it flexed under heavy stress, where rust liked to hide. Reliability didn't come from maintaining a pristine, out-of-a-boxed condition. It grew from an intimate familiarity with imperfection. This philosophy of overbuilding extended deep below the waterline, into the parts no passenger ever saw. Shafts were thicker than calculations demanded. Bearings were designed to be forgiving. Tolerances were wide enough to accommodate wear, heat, and the inevitable misalignment that comes with a hard life. An engine could run rough, sound loud, and be horribly inefficient and still run, and that's what mattered. A machine that performs beautifully until it suddenly doesn't is impressive in a brochure. But a machine that can limp you home while sounding like it's dying is a lifesaver. The designers of that era accepted a simple truth: components would degrade. Instead of fighting that reality, they planned for it. They built corrosion allowances right into the thickness of the steel. They sized wooden structures, knowing that rot would eventually claim a piece of it. Fasteners were made accessible, removable, and replaceable. Nothing was sealed away forever, because nothing was trusted forever. Maintenance wasn't an afterthought. It was assumed, constant, and expected. Even the very shape of these older ships reflected this mindset. Their fuller hull forms sacrificed raw speed for incredible stability. A ship that rolled slowly and predictably was kinder to itself and its crew. These slower motions reduced fatigue in both the metal and the bones of the people on board. The ship was designed to absorb the ocean's energy, not to challenge it head-on. Modern eyes might call these hulls blunt or inefficient, but blunt things break less often. There's a reason old ships can look so calm, even when the seas around them are anything but. The reliability of old ships also came from a refusal to chase theoretical limits. Engines were rarely pushed anywhere near their maximum output. Boilers loafed along well below their rated pressure. The electrical systems were simple, direct, and lightly loaded. They kept heat, stress, and vibration within conservative, comfortable bounds, because everyone knew that those forces were the true killers over time. Nothing fails dramatically if it never lives on the edge. And then there was redundancy, but not the optimized, clean redundancy of modern systems, where one identical component backs up another. This was a messier, more organic, and more resilient kind of redundancy. Different systems could accomplish similar tasks. If the powered steering failed, sheer muscle could still move the rudder. If the engines died, there were still sails, anchors, or drift tactics to rely on. If the fancy navigation instruments were lost, the sky still spoke a language the crew could understand. Reliability wasn't centralized in one black box. It was distributed across the entire ship and the people who sailed her. Crucially, old ships were designed to be understood. You could trace a pipe with your hand and know exactly where it went. You could listen to an engine and know if it was happy. Your sense of smell told you just as much as the gauges did. This was vital, because detection is half of reliability. Failures that announce themselves early are survivable. Failures that happen silently are deadly. Old ships were noisy, smelly, and incredibly communicative. They told you when something was wrong, and they told you loudly. And the sea rewarded this approach. The ships came back, battered but intact. They returned with stories etched into their hulls, with systems that had been stressed but not exceeded their limits. Their crews trusted them, not because they were perfect, but because they were honest. When something did break, it usually broke slowly, giving the crew precious time for reaction, improvisation, and repair. In the end, old ships were reliable not because they were romantic or primitive. They were reliable because they were built under the stark assumption that no one was coming to save them. They carried their own solutions, their own margins for error, their own forgiveness for the harsh realities of the world. They expected the worst and prepared accordingly. And when the ocean tested them, as it always does, that expectation often made the difference between a long, hard night and a final one. Have you ever wondered what made those old, clunky ships, the ones from the age of steam and steels, so incredibly dependable? It wasn't just the materials they were made of. It was something deeper, a relationship between people, metal, and machinery, built on a foundation of visibility and consequence. On an old ship, nothing was abstract. Everything was real, tangible, and honest. Materials behaved exactly as you'd expect. Iron rusted where water collected. Wood swelled and shrank, and you could hear it groaning under strain. Steam hissed, oil seeped, and the vibrations from the engine room traveled right through the soles of your shoes and into your bones. Every single system on the ship was constantly announcing its condition, and a good crew learned to read these signals, just like a farmer reads the weather in the sky. This mechanical honesty was crucial because it kept humans in the loop. Old ships didn't hide their complexity behind sealed black boxes or layers of software. A pump was a pump. You could see it, touch it, understand it. A valve was a valve. If something broke, it usually failed in a way you could see, hear, or feel. A bearing would run hot long before it seized up completely. A boiler would leak steam as a warning before it ever burst. A generator would sputter and cough before it died. These weren't sudden surprises, they were warnings. And real reliability is built on warnings. The crews on these ships weren't just passive operators pushing buttons on a console. They were caretakers, engaged in a continuous dialogue with their vessel. Engineers knew the unique personality of each engine, how it sounded when it was cold, how it smelled when it was being pushed too hard, how the vibration changed when its alignment started to drift. On deck, officers knew how the hull felt moving through the water, how the ship responded to the rudder in a crosswind, and exactly how much of a beating she could take before she started to show signs of fatigue. This wasn't theoretical knowledge from a textbook. It was experiential wisdom, built up over years at sea, not through a software update. The very materials used in these older ships played a part in their resilience. The steel was often softer, more ductile. It wasn't optimized for being lightweight. It was made to be forgiving under stress. When it was pushed to its limits, it would bend long before it shattered. Even the riveted construction, which we might laugh at today, had a hidden advantage. A crack in the hull struggled to spread across a riveted seam. If one rivet failed, it didn't cause the whole structure to unzip. The damage stayed local, manageable, and survivable. Early welded ships learned painful lessons about brittle fractures that older construction methods had avoided through tradition and, frankly, a bit of luck. And where wood was still used, it was just as instructive. It absorbed shocks, dampened vibrations, and failed gradually. A cracked beam would groan a warning. A worn plank would flex noticeably. Repairs were straightforward because the materials were familiar. You didn't need proprietary tools or a sterile, sealed environment to fix things. A hammer, a wrench, a welder or, sometimes just brute strength, and a clever idea were often all you needed to keep the ship going. This idea of transparency extended to the very layout of the ships. Systems were spaced out generously. Access was a priority. If something broke, you could actually get to it without having to dismantle half the ship. That extra space was a form of insurance. Modern design often crams everything together for efficiency, but that compression can hide problems and make repairs a nightmare. Old ships were designed with the assumption that things would break, and that repairs would have to be done underway, in rough seas, by tired hands. So they left room for people to work, not just for machines to fit. Crucially, the human element wasn't seen as a problem to be engineered out of the system. It was treated as a vital resource to be trained and trusted. Crews were larger, not just because the work was more labor-intensive, but because having redundant people was just as important as having redundant equipment. Knowledge was distributed throughout the crew. If one engineer was out of action, another could step in. If the captain was incapacitated, someone else knew the ship well enough to bring her safely back to port. Training reflected this reality. Sailors learned the principles behind how systems worked, not just the procedures for operating them. This meant they could improvise when the unexpected happened, and at sea, the unexpected always happens. They could reroute a pipe, repurpose a pump, or bypass a broken system with creativity, without needing to consult a manual that was written for ideal, perfect conditions. This is where true reliability shows its face. A system that only works perfectly under ideal conditions is fragile. A system that can still function, even badly, under terrible conditions, that's a reliable system. Old ships accepted that things might get ugly. Engines ran dirty. Repairs could be crude, but they worked. A temporary fix might become permanent if it held up. The crew's pride wasn't in the elegance of their solutions, but in their endurance. There was also a powerful sense of accountability built into this culture. When something failed, it wasn't blamed on a mysterious algorithm or an opaque subsystem. The failure was examined, understood, and remembered. The lessons learned were passed down through word of mouth, in logbooks, and through shared stories. A near miss became a cautionary tale, told to every new crew member, not just a forgotten data point in a report. This storytelling was incredibly important. It shaped behavior and reinforced caution in a way no spreadsheet ever could. Some people might look at this old world and see it as less advanced, but in reality, it was advanced in a completely different way. It was advanced towards resilience, not just optimization. The goal wasn't to eliminate human involvement. It was to amplify human judgment. The ship was an extension of the crew, and the crew was an extension of the ship. Reliability grew out of that deep partnership. Even maintenance followed this natural rhythm. It was constant, hands-on, and preventive. Crew members walked their spaces every single day. They touched surfaces. They listened for strange noises. They smelled for unusual odors. They simply noticed things. Small issues were fixed before they could grow into big ones. Today, we often rely on scheduled maintenance or automated sensor alerts. Old ships relied on human attention. Attention might seem inefficient, but it is profoundly effective. When failures did happen, they were rarely total. Systems degraded gracefully rather than collapsing all at once. This gave the crew something incredibly precious: time. Time to respond, to adapt, to survive. Catastrophic, instantaneous failures were rare because very few systems were pushed to the absolute edge of their tolerance, and they weren't so tightly interconnected that one fault could bring down the entire ship. In this world, reliability wasn't a number calculated after the ship was built. It was a way of life, something practiced every single day. It grew out of familiarity, a sense of humility before the power of the sea, and the acceptance that humans would always be part of the equation, always imperfect, but always necessary. Old ships didn't try to protect themselves from people. They relied on them, and for a very long time, that mutual reliance worked extraordinarily well. Have you ever looked at an old ship and wondered why it looks so simple? It wasn't by accident. That simplicity was a deliberate choice. a hard-won lesson learned over generations at sea. It was a feature, not a bug, and the reason was simple: simplicity works. Every new system added to a ship, no matter how clever, was another potential point of failure, another thing that could break at the worst possible moment. So, restraint became a form of safety. Designers and sailors learned that a ship doing fewer things could usually do them for longer, and under much harsher conditions, than a ship trying to do everything perfectly. Take speed, for example. Old ships were slow, no doubt about it, but that slowness was a gift. The mechanical loads were gentler, the vibrations were lower, the engines warmed up and cooled down gradually, instead of being yanked from one extreme to another. The hulls didn't slam into waves as violently. Bearings, gears, and all the moving parts lived longer, happier lives. Fatigue built up slowly, almost politely. Nothing was ever rushed, because nothing mechanical enjoys being rushed. This deliberate pace was reinforced by manual controls. Steering a ship took real physical effort. Moving the throttle was a deliberate act. Valves would resist being opened too quickly or too far. This friction, this physical resistance, was a form of feedback. It was a constant reminder that you were applying force to something real, something tangible that could be damaged if you pushed it too hard. Modern interfaces are smooth, effortless, almost digital illusions. They hide the consequences. On an old ship, the consequences were right there in your hands. This philosophy of simplicity also meant that systems were kept separate. One failure didn't immediately cause a chain reaction. Electrical systems were often minimal, sometimes just for lights and basic communication. The main engine didn't need a computer to run. Navigation wouldn't collapse if the power flickered for a second. This separation was crucial, because complexity creates connections, and those connections create fragility. Old ships didn't just compartmentalize their physical spaces, they compartmentalized their functions. There was also a deep-seated resistance to automation. It wasn't because sailors didn't want help, but because automation can remove awareness. An automated system works beautifully right up until the moment it doesn't, and when it fails, it often fails silently or with no warning. Manual systems, on the other hand, demand your constant attention. They keep you engaged, and while being constantly engaged is exhausting, being disengaged is downright dangerous. Old ships chose exhaustion over danger. This doesn't mean technology stood still. It just means new technology was adopted with extreme caution. It was tested, observed for years, and only integrated when its potential failures were thoroughly understood. A new piece of machinery had to earn its place on board. If it introduced unpredictable behavior, it was fundamentally distrusted. In that world, trust was slow to build and incredibly easy to lose. Reliability was part of the culture long before it was a technical specification. Operating procedures reflected this same sense of restraint. Ships rarely ran at their absolute maximum capacity unless it was an emergency. Captains avoided bad weather when they could, rather than trying to challenge it head-on. Decisions leaned towards conservatism because there was absolutely no reward for seeing how close to the edge you could operate. The ocean has never rewarded bravado. It has only ever punished it, patiently and without fail. Even the emergency systems were designed for simplicity. Fire suppression was direct and intuitive. Flood control relied on muscle and gravity, just as much as on machinery. Life-saving equipment was rugged, obvious, and overbuilt. In a crisis, you don't want to be interpreting a complex manual. Clarity saves lives, and clarity is born from simplicity. Communication was just as direct. Orders were shouted, repeated back, and confirmed. There was no room for ambiguity about who was responsible for what. The chain of command was clear, and so was accountability. When something went wrong, it was dealt with immediately, by people, not deferred to some abstract system or process. Responsibility remained human. The result of all this was a ship that could take a beating without betraying its crew. Of course, things still broke, but they usually broke one at a time. Repairs were often ugly, patched-together affairs, but they were effective. Workarounds weren't just possible, they were expected. There was always another way to keep going, another way to limp back to port. This adaptability is the quiet, unsung hero of true reliability. Modern thinking often sees simplicity as a lack of something, as an obstacle to be overcome with clever engineering. But the sailors of old saw simplicity as a shield. They understood and accepted their limits and worked within them. By attempting to do less, their ships were able to endure more. This wasn't just nostalgia or being stuck in the past. It was pattern recognition, pure and simple. Generation after generation of seafarers watched complex systems fail first and fail hardest. They saw that the ships that survived the longest were the ones that asked the least of their components. Over time, this practical wisdom hardened into tradition, and that tradition became embedded in the very design of the ships. By the time newer vessels began chasing efficiency as their ultimate goal, the old-timers had already proven something quietly radical, that reliability doesn't come from adding more and more capabilities. It comes from systematically subtracting vulnerabilities, and subtraction, when it's done well, requires immense discipline. As the world changed, demanding faster schedules, tighter profit margins, and greater cargo capacity, the pressure to abandon this philosophy of restraint grew. Efficiency promised more profit, more speed, more everything. But efficiency is a jealous master. It demands that everything else, including simplicity and redundancy, step aside. The sea, however, doesn't care about our spreadsheets or our delivery schedules. The sea doesn't notice efficiency, it only notices what breaks. And in that unforgiving environment, the lessons of the past remain as true today as they ever were. Efficiency didn't just show up one day, announcing itself as the villain of the story. No, it was much subtler. It arrived politely, dressed in the sharp suit of progress, carrying spreadsheets and promises of a better future. Fuel could be saved. Crews could be smaller, turnaround times in port could be slashed, sensors could watch what human eyes once did, software could now make decisions that once required seasoned judgment. Taken one by one, each of these steps made perfect sense. And that, right there, was the danger. Reliability is rarely lost in one single, dramatic decision. It's traded away, piece by piece, in dozens of seemingly reasonable choices. Modern ships are, without a doubt, brilliant machines. They are optimized down to the last kilogram and the final kilowatt. Their hulls are sculpted by computers for the absolute minimum resistance against the water. Their engines are tuned to operate within very narrow bands, where emissions and fuel consumption look beautiful on paper. All the systems on board are constantly talking to each other, sharing data, synchronizing actions, and coordinating responses faster than any human ever could. And on calm water, under ideal conditions, this brilliance is undeniable. But brilliance can be brittle. Optimization, by its very nature, removes the margin for error. When you design a system to operate right at the edge of its peak efficiency, you leave very little room for surprises, for wear and tear, for contamination, for the unexpected. Old ships were different. They carried excess capacity like fat reserves for a long winter. Modern ships are more like lean athletes, incredibly strong and fast, but also incredibly vulnerable when something goes wrong. A single clogged sensor, a corrupted data signal, a minor software mismatch, these things don't just degrade performance gradually anymore. The failure can be sudden and catastrophic. Automation has profoundly changed the role of the humans on board. Crews have shifted from being active participants to being supervisors. The complex systems run quietly, invisibly, doing their work behind user interfaces that are specifically designed to reduce the human workload. And this works wonderfully. Until it doesn't. When something abnormal happens, the human operator is suddenly expected to jump in and instantly take control of a system they may not have physically interacted with for months. The muscle memory is gone. The subtle sensory cues, the sounds, the vibrations are gone. Their deep understanding has faded into a series of abstract icons on a screen. Cost pressure has amplified every single one of these issues. The global shipping industry is ruthlessly competitive. Every extra crew member is a line item on a budget. Every additional ton of steel is more fuel that has to be burned forever. Maintenance is no longer done when needed. It's scheduled, optimized, and sometimes deferred. Components are replaced when a metric on a screen says they should be, not when an experienced engineer feels that something is off. On paper, it all looks perfectly rational, but in the real world, it means that small, human-noticed irregularities are often ignored because they haven't yet crossed a digital threshold. Specialization has replaced general competence. As crews shrank, so did the redundancy of knowledge. You now have one person who knows one system inside and out. If that person isn't available for some reason, that entire system becomes a black box. Training has shifted from teaching principles to enforcing procedures. Manuals have gotten thicker, and checklists have multiplied. So when a system behaves in a way that isn't on the checklist, improvisation becomes harder, not easier. The very materials used to build these ships have also played their part. Modern high-strength steels are marvelous. They're light, strong, and can be formed into precise shapes, but they fail differently than old steel. They don't always bend and groan, giving you a warning. They can crack, and that crack can propagate until the failure is sudden and clean. Composite materials add incredible strength and efficiency, but can hide damage internally, where you can't see it. Of course, sensors are supposed to catch this sort of thing. But sensors are just another system, and they can fail, they can misread, or they can flat out lie. When your detection of a problem becomes indirect, your certainty erodes. The tight integration between all these systems has also changed how failures happen. Electrical power, for example, is no longer just a convenience. It's a fundamental dependency. If you lose power on a modern ship, you can lose steering, navigation, pumps, and communications sometimes all at once. Yes, there are redundant systems, but they are often just identical twins of the primary system, which means they are vulnerable to the exact same flaw. Old redundancy was messy and complicated. Modern redundancy is elegant and clean, which also means its failures are correlated. At the same time, speed is returned as a top priority, and with it comes stress. Engines are cycled faster, loads on the hull spike harder. The tight schedules leave very little room to slow down for bad weather or to give the machinery a break. The ship is expected to perform consistently, no matter the conditions, and when performance becomes an obligation instead of a choice, caution becomes a liability. There's a psychological shift that happens. Modern systems inspire confidence precisely because they are so good right up until the moment they aren't. This confidence can easily slide into complacency. When a system has worked flawlessly for years, our trust in it replaces our vigilance. Old ships never allowed for that kind of complacency. They were constantly reminding their crews that things could go wrong, because small things were always going wrong. Paradoxically, this constant stream of minor trouble kept everyone sharp. So when failures do happen on modern ships, they often feel shocking and completely out of proportion. A single fault cascades through the network. A simple misconfiguration disables multiple safeguards at once. The crew is suddenly asked to diagnose a complex digital problem that has very real, analog consequences, all while under extreme stress and with incomplete information. Reliability didn't just disappear, it changed its character. It became conditional. Confirmation bias reinforces this shift. Because modern ships work perfectly almost all of the time, when one doesn't, the failure is often treated as a bizarre anomaly rather than a systemic warning. Lessons are localized, the paperwork is updated, and the broader system continues on, unchanged. Old ships accumulated wisdom through their scars. Modern ships often bury that wisdom in reports. Now, none of this is to say that modern designers are careless or ignorant. They are responding to powerful incentives, economic, regulatory, and environmental. Efficiency is demanded. Emissions must be reduced. Costs have to fall. Automation isn't an option. It's an expectation. The tragedy is that reliability doesn't make a grand announcement when it's being quietly sacrificed. It only speaks up when conditions are at their absolute worst. And the ocean, unchanged and utterly indifferent, is always waiting for those conditions. Modern ships are not unreliable because they are poorly built. They are unreliable in very specific ways because they are too precisely built for a world that refuses to be precise. They assume a level of predictability that the sea simply does not offer. What we've truly lost isn't competence, but forgiveness. Old ships forgave mistakes. They forgave abuse and ignorance to a remarkable degree. Modern ships forgive very little. They expect correct inputs, clean data, perfectly maintained tolerances, and compliant operation. When those expectations are met, they excel. But when they're not, the margin between control and crisis can shrink to a matter of seconds. This is the quiet trade that lies at the heart of modern shipping. We exchanged astonishing capability for a narrower window of survivability. The ships are smarter, the systems are faster, the economics are tighter. And somewhere along that path, reliability stopped being a cultural obsession and became a statistical assumption. But the sea has not adjusted its expectations accordingly. The ocean has an inconvenient habit of teaching the same lesson over and over, regardless of how many times it's ignored. It teaches that reliability isn't a feature you install, but a posture you adopt. Old ships embodied that posture without even naming it. Modern ships, for all their incredible sophistication, often struggle to remember it. What this contrast reveals is that reliability is cultural before it is technical. It lives in what designers fear, what operators expect, and what entire organizations reward. Think about it. Old ships were born from a culture that assumed isolation, scarcity, and consequence. When you were out there, you were on your own. Help was a distant, uncertain concept. Mistakes were incredibly expensive, sometimes costing everything. That stark reality shaped decisions long before a single piece of steel was ever cut. Now, fast forward to today. Modern ships are born into a culture of constant connectivity, optimization, and rescue. Satellites watch their every move. Global support networks exist. Systems are monitored remotely from thousands of miles away. The entire psychological environment has changed, and ships reflect that change just as surely as they reflect advances in metallurgy or computing. The lesson here isn't that the past was better or that progress was a mistake. Not at all. It's that something essential was once understood intuitively, and then we gradually externalized it. Old ships carried responsibility within themselves, in their very design and the crew's mindset. Modern ships, however, tend to distribute that responsibility outward to software, to complex procedures, to shore-based systems, and to a general assumption that everything will be normal. When everything works, this distribution is brilliantly efficient. It's a marvel of modern logistics. But when things break, it becomes dangerously ambiguous. Who or what is truly in charge? A key difference is this. Old reliability came from expecting degradation. Modern reliability often assumes correctness. That might sound subtle, but it's a profound distinction. A system designed for degradation plans for wear and tear, for human misuse, for misunderstanding. It's built to be forgiving. A system designed for correctness assumes compliance. It expects every part, every person, every line of code to behave exactly as planned. But the ocean doesn't comply. The ocean degrades everything relentlessly, without any regard for our design intentions. Then there's the constant tug-of-war between robustness and efficiency. They aren't opposites, but they absolutely compete for attention. Old ships gave robustness the top priority and accepted inefficiency as a necessary cost of survival. Modern ships, under immense economic pressure, have inverted that priority. Neither approach is inherently wrong, but this inversion carries a risk that is so easy to underestimate because it accumulates invisibly, layer by layer. A margin shaved here, a redundancy aligned there, crews reduced just a little more each decade. No single decision feels reckless on its own, but the sum of them can be. And what about the human element? This is a huge part of the story. Old ships treated humans as essential components, as the primary sensors, actuators, and decision-makers, deeply embedded in the system. Modern ships, on the other hand, increasingly treat humans as exceptions. They are the interveners called upon only when the automation fails. This is a fantastically difficult role to play. Skills decay without regular use. Judgment dulls without constant engagement. When you ask people to suddenly become sharp and decisive after long periods of passivity, errors are almost inevitable. Reliability suffers not because people are incompetent, but because the system itself has quietly trained them to be less involved. The stories the sea keeps repeating often sound eerily similar. A small fault goes unnoticed because it's masked by automation. A system behaves unexpectedly when pushed outside its design envelope. Recovery is delayed because understanding what's happening lags far behind the events themselves. What once would have been a manageable inconvenience escalates into a full-blown emergency because the margins are razor-thin and all the systems are so tightly coupled. These aren't moral failures, they are systemic ones. Old ships didn't magically eliminate these risks, but they mitigated them through three powerful tools: slowness, transparency, and forgiveness. They bought time, time to notice, time to think, time to act. At sea, time is the ultimate currency of survival, and old ships were wealthy in it. Modern ships, all too often, are operating on credit. Perhaps the most enduring lesson is that reliability cannot be fully outsourced to design. It can't be just a feature on a spec sheet. It has to be practiced, daily. It must be felt. It must be remembered. Old ships forced this practice through their constant, minor imperfections. They were always demanding attention, always needing a tweak or a fix. Modern ships often hide their imperfections until they become severe, and in doing so, they remove those crucial opportunities for learning, for staying sharp. Now, none of this is a call for a return to rivets, steam engines, or the future is not behind us. But the mindset that made old ships so reliable is portable. It's a philosophy we can bring with us. Margin can be reintroduced deliberately into our designs. Simplicity can be protected where it matters most. Humans can be kept meaningfully in the loop, not as passive backups, but as active partners with the technology. We can design systems to fail slowly, loudly, and locally, rather than silently and catastrophically. The ocean will continue to test our creations without any regard for their era or their technology. It will exploit our assumptions, reward humility, and punish arrogance with an equal, chilling indifference. Old ships survived so well because their designers and crews assumed nothing and prepared for everything. Modern ships, at their very best, still do this. But at their worst, they forget why that assumption of fallibility mattered so much in the first place. Reliability isn't nostalgia. It's memory made structural. The old ships remembered the sea in their very bones. The question the ocean keeps asking, with every wave and every storm, is whether the new ones do, too. Thanks for watching. If you found this interesting, consider subscribing for more deep dives into the world around us. Stay curious,